Hi guys. Okay, so let's look at the limiting reactant problem. First of all, let's look at a real life example of a limiting reactant problem. So here I want to have a sandwich which has a jam spread in it. Okay, so I have this huge big bottle of jam, lots of jam. Okay, and I just have these two slices of bread. These two slices of bread. Two slices of bread and this huge amount of jam. No matter how much jam I have, I can only have one sandwich if I want to, right, like a decently tasty sandwich. So I can only have one sandwich. So the final product here is the sandwich, and these slices of bread are the reactants, and this is another reactant, right? So I am limited by the amount of slices that I have, and I can only get one sandwich out of it. Okay, so this is one story. Next story is, if I have this large amount of bread, let's say, for example, all these pieces of bread I have, and let's look at it this way. Okay, just keep that one. Okay, so these are the 4 pieces of bread I have. Okay, and I just have this 1 spoon of of jam. So 1 spoon of jam and all this excess bread, how many sandwiches can I get? As much as this bread is going to allow me, maybe just 1 sandwich, right? So here, again, I'm limited by the amount of sandwiches that I can get depending upon how much jam I have. So jam is the limiting reactant now. So in the previous case, it was a bread, a limiting reactant. In the second case, it was a jam. So it varies, and we use the limiting reactant problems in our daily life, specifically if you're working in the kitchen or working in the industry. You make these determinations. How much of the starting material do you need if you want a certain amount of product? So let's look at the same concept, how it is applied in the chemical reactions. Okay, all right, just a minute. Okay, so now we are going to be looking at this problem of nitric oxide reacting with hydrogen to give you ammonia and water. And here we are trying to determine how much of the ammonia can be produced from a given amount of nitric oxide and a given amount of hydrogen. So really the comparison is between the nitric oxide and ammonia and hydrogen and ammonia. Okay, so give me 1 minute. Okay, so now we are given 45.8 grams of nitric oxide and 45.8 grams of nitric oxide. And another thing that we are given is 12.4 grams of hydrogen. Okay, so we need to find out how much of ammonia can be produced when each of these reactants are used. Okay, now the way you're going to set up this problem is, first of all, you're going to check always whether your equation is balanced or not. So as you can see, 2 moles of nitric oxide is reacting with 5 moles of hydrogen to give you 2 moles of ammonia and 2 moles of water. So the relationship of nitric oxide and ammonia is 2 to 2, and the relationship of hydrogen and ammonia is 5:2. That's at the molar level. So first is, you're going to set up the problem. The general, I'm going to just write down a very general scheme. That is, every time you are given the grams, you always need to convert that to moles, and the grams are converted to moles using the molar mass as the conversion factor. Okay, so once you get the moles, the next step is to look at the mole to mole ratio. That is the moles of one over the moles of the other. Now let us assume that you are looking at the moles of A, okay? Grams of A, you convert that to grams of A. So here is going to be the moles of A. and you will, this way you're going to convert it to moles of B from the mole to mole ratio. And then comes the next step. Once you get the moles of B, you're going to convert them to the grams of B. And how are you going to do that? You're going to use the molar mass of B. So this gives you the grams of B, and here this goes through the molar mass of B. Okay, so this is the molar mass of B, and that's going to give you the grams. So we have, this is the molar mass of B, and here is the molar mass of A. Okay, so this is our general scheme. So now let's do the comparison of nitric oxide. So let's compare 45 grams of 45.8 grams of nitric oxide, and let's see how much of the ammonia it is producing. So the first step is going to convert to moles. So 1 mole of nitric oxide, and sorry, this is the nitric oxide, NO, 1 mole of nitric oxide. The molar mass of nitric oxide is 30.01 grams. Okay, 30.01 grams. So that's for the nitric oxide. So that's the nitric oxide, moles of nitric oxide. Next, you can proceed from here only. Next is you take the moles of nitric oxide from the equation, and in the reaction, as you can see, the 2 moles of nitric oxide is giving you 2 moles of ammonia. So here you're going to write down 2 moles of nitric oxide and 2 moles of ammonia. Okay, because you need to convert the moles of nitric oxide to the moles of ammonia. Okay, nitric oxide to the moles of ammonia. Next, the question is asking clearly how many grams of ammonia can you produce? So now what you're going to do, you're going to put 1 mole of ammonia in the denominator, because now you want to cancel out those moles of ammonia, and you're going to put the molar mass of ammonia, which is 17.4. Okay, so molar mass is something you need to calculate on the side on your own. So next is that you are going to cancel out, and you will see, as you can see, I'm going to use this color. So grams of nitric oxide and the grams of nitric oxide cancel out. Moles of nitric oxide and the moles of nitric oxide cancel out. The moles of ammonia and the moles of ammonia cancel out. And we are left with now 45.8 times 1 times 2 times 17.04, and this is going to be grams. That's grams over 30.01 times 2 times 1. And this whole thing is going to give you 26.0 grams of ammonia. Okay. Next is you have, this is a case 1 when you use, this is with ammonia, with nitric oxide. Okay. Next is you're going to write down for the hydrogen. Okay. So for hydrogen, you're going to take the amount given, which is 12.4 grams. So we have 12.4 grams of hydrogen. First step is to convert it into moles. So we know that 1 mole of H2, so pay attention, it's H2, okay, is 2.02 grams. Now that is the molar mass of hydrogen, okay, H2. Okay, next is the mole to mole ratio, and that mole to mole ratio we see is the 5:2. So 5 moles of hydrogen in the denominator, and that's what we need to get rid of, and we are getting and we're going to put the 2 moles of ammonia. So 2 moles of NH3 is going to be on the numerator. Next, you're going to convert the moles of ammonia. So this is the molar mass. So moles of ammonia, 1 mole of ammonia is 17.04 grams of ammonia. Okay, 17.04 grams of ammonia. So here we have the situation where the grams of hydrogen and the grams of hydrogen cancel out, the moles of hydrogen and the moles of hydrogen cancel out, moles of ammonia and the moles of ammonia cancel out, and you're just left with the grams of ammonia. So now we do the calculations, which is 12.4 times 1 times 2 times 17.04 divided by 2.02 into 5 into 1. And this gives you 41.8 grams of ammonia. Okay. So now comes the question, which one is giving you less? 41.8 grams is less, or 26.0 grams is less? So you are obtaining the lesser amount from the nitric oxide. So therefore, nitric oxide is going to be your limiting reactant. Okay, so limiting reactant here is limiting reactant is nitric oxide, because it allows us to give, because it allows us to have less of the ammonia, and that ammonia is 26.0 grams of ammonia. And this is in reality, excuse me, this in reality is the theoretical yield. So this is, in theory, this is the theoretical yield. Okay, you won't be able to produce anything more than that. In fact, actual yield is even lesser. So, but anyways, I hope that was easy, and just pay attention to the limiting reactant is the product which is obtained less. So whichever reactant gave you the less product is the limiting reactant. Okay, so I hope that was easy, and thank you for watching. Bye-bye.